ladies and gents, welcome back to more interesting maths. I've decided I do want to shift back to the GCSE maths just for a little while, partly because I brought out a video last week looking at a puzzle that I really enjoyed, and it turned out that there was a lot of what are known as combinatorics involved. I gave a very quick listen on that during the video, and lo and behold, Frosty's actually got a set of slides on it. Today, I want to take you through those. Over the next few weeks, I'm hoping to release a few more videos that look at the different uses of number. Why? Because I'm an unashamed nerd, and I'm really looking forward to bringing out different videos on counting strategies, working in different bases. This is pure nerd material, and I'm not sorry for any of it. So here we have what are known as counting strategies. Now, counting strategies may sound a little bit weird. At home, you will be used to going, yes, I can go 1, 2, 3, 4. Do I need another way of counting? And the short answer is, yes, you do. Because certainly if you're looking at computing or task management or the different ways that something can be done, you need something slightly easier than going 1, 2, 3, 4, 5. It's a huge part of combinatorics, it's a huge part of programming, business management, pick anything you want, combinatorics will make it into the higher levels. So, without further ado, let's learn how to count. We have two different forms. There's what's known as systematic counting, which is effectively listing, and then there's counting by multiplying. We'll go through both of those as we head out. Let's have a look, oddly enough, in part 1, at part 1. As I pointed out, sometimes you might want to list every single possibility, but there are different ways of doing it. So in these two scenarios, for instance, we've got a team of one boy, one girl. The boys are Adam, Bob and Charles, the girls are Diane and Elaine. What are all the possible choices of the team? Nice little hint here, GCSE questions and usually A-level questions and so on will make it fairly convenient for you to delve a little deeper or make life a little bit easier by saying you can write A for Adam, B for Bob, C for Charles. So let's have a look at all the different places. We've got Adam and Diane, Adam and Elaine, Bob and Diane, Bob and Elaine, Charles and Diane, Charles and Elaine. The easiest way to do that, certainly if you're given two options, is go through it. This is what's known as the systematic nature of it. We look at each element in turn. So say, for instance, we've started with Adam. Adam could go with Diane or Elaine. So we write those out to begin with. Then there's Bob. Bob could be with Bob or Elaine. Charles could be with Diane or Elaine, and so on. That is a systematic way of doing it. It's effectively, rather than just picking them at random, as in Adam and Elaine, Bob and Diane, Elaine and Charles. If you did it that latter way that I've just done, it becomes very tricky to see whether or not you've got all of the combinations, whereas a systematic method that you can get into the habit for yourself will make it fairly easy to know whether or not you've got it. Now, the thing to notice about the number of people, the number of combinations that we've had, is that there are in fact 6 of them. Now, notice that we had 3 boys and 2 girls. 3 times 2 is 6. So in our head, we should have been thinking from the offset, there's going to be 6 different combinations, and we'll see how that comes in later on. This one's a lot more interesting. Frog with 6 lily pads in front of him, he can either hop onto the next lily, or he can skip one, meaning he can hop from 1 to 2 or 3 to 4, or he can skip from 2 to 4 or 3 to 5 and so on. Now we have to list out all the sequences for the frog to get to the final lily pad, and it's helpful to notice that there's 6 of them. Now on the face of it, that doesn't seem so easy. Again, it's tempting to think that there's loads and loads and loads and loads and loads of different options. So we start with the most basic option. I mean, personally, I would write the numbers 1 to 6 at this point and start to think about it. So the most obvious way we could start with is a hop, 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 hop. I think I said that enough times. As in, the most basic element would just be to hop to each lily pad. The alternative of that would be, given that there are 6 of the lily pads, we could just go skip, skip, and skip. That would take us to 2, to 4, and to 6. So is there a way of going from 6 skips down to 3 hops? Now we notice again, all of them have to add up to 6. So we can treat it effectively as a combination of 1s and 2s. So how do we do this? I think I've got that no, I did have it the right way around. What we do is look at the number of skips. Because again, bearing in mind it all has to add up to 6, we can say 0 skips, all the hops. There's only one way we can do that. Now, if I skip one, that means that I can only have 4 hops. Hop, 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 and a skip. That gives us our 6 jumps, and they can go in wherever we like. That could go in right at the start, that could come after the first hop, the second hop, the third hop, and the fourth hop. And finally, it could come in right at the end. So that's 5 ways to do that. What about 2 skips and 2 hops? Again, 2 skips, that would give us an account for 4, which means we could only have 2 hops. This is the systematic method. This is looking at it in one certain fashion. So what we do next is we say, right, okay, well, I'm going to start with 2 skips and a hop. Then I'm going to swap them around, so skip, hop, skip, hop. Well, what if I did that the other way? Hop, skip, hop, skip. That'd be fine. And you can see that we've broken them down. I'm not going to bore you with all of the detail, but here they are in the 6 given fashions, and you can see for yourself whether you've got them right. And then what do? We just count the different ways that we've included them. So there was 1 way to do all the hops, 1 way to do all the skips, 5 ways with 1 skip, 6 ways with 2 skips. We add those all together, and we get 13. It's about breaking the problem down. It's tempting, certainly if you're at GCSE level or maybe A level, to get a little bit impatient, to think, well, I must have included all of them. If you break it down in this way, you make life so much easier. So similarly, again, as always, test your understanding with this. I will assume that you have paused it. I'm just going to chat right the way through. Here we've got the figure with the rectangle PRSU standing for the corners, and you can see that we've got it split into 2 distinct squares using the line Q and T. How many right-angled triangles can be drawn using any of the 3 points? Now, these pictures, if you're watching this at the time of coronavirus, these have been going mental. These are the pictures on Facebook with loads of different triangles saying how many triangles can you construct from that. This is exactly the same thing. This is what the counting is designed to help us do. How can we systematically find a way to break down that rectangle? And I think the answer is incredibly elegant. First off, look on the left-hand side. There's these small triangles. We can just cut the square, each square, into a very small right-angled triangle. It's also an isosceles right-angled triangle, but we'll save that for later. And then how many of them are there? Well, looking at this square here, you could get a right-angled triangle from corner U, from P, from Q, or from T. But the same can be true from the other side, which is why we've got 8 of those. That aside, we can forget about it. Why? Because we've reasoned out all of the smallest right-angled triangles. So we draw a little diagram, times 8 underneath. That's perfectly fine. Well, what if we extended that right angle into the other corner? So from P to U to S. We can see that we've got 4 of those because they take up the entire rectangle. So there's only 4 of those. And then finally, it takes a keen eye to notice these last 2, so that is where your reasoning comes into play. But you'll notice each of these angles are 45 degrees. What does that mean? This angle here at the top must also be 90 degrees. Of which there's 2 of them, because we can flip that triangle upside down. So what do we have? 8 plus 4 plus 2, 14 different ways to draw a right angle triangle. That's the systematic counting. I will pause the video for now and leave it to you, because I'm aware that my face is sat in the right-hand screen, so you won't be able to see question 4 at the minute. As always, what I'm going to do is pause the video, but it'll come in 2 parts now, because there are exercises on the next slides, and I don't want to deprive you from any of those, but I'll reveal the answers in sequence as we go along. So there you are, folks. A brand new method of counting. Now, the video that should hopefully come out the day after you've seen this one, so today's date +1, if not it's already out, is counting part 2, counting by multiplying. That doesn't necessarily give us the explicit answers or all of the combinations that we could be looking at, but it's a very neat and elegant way of telling us all of the different combinations that we might be having to look for. Until then, you're absolutely awesome. Take care.